Hi, welcome back. So in this video series, we're gonna cleaning up my mess. In this video series, we're gonna be discussing the remainder of the vector calculus course. So now we're gonna get into the proper subject of vector calculus. So previously we discussed what a vector field is, as well as scalar functions, right? Scalar functions, vector field functions, scalar fields and vector fields. And I said that this corresponded to something like a scalar and a vector that you learned in linear algebra. Well, of course, this is a calculus course, so we need to connect these concepts to calculus. And what sort of things do we do in calculus? Well, we do mostly derivatives and integrals, right? So computing rates of change and computing volumes and areas and things like that. So let's get right into it. Okay. So let's consider an arbitrary curve, right, in two-dimensional space. I don't know if you can see that. Okay, so you have this arbitrary curve in two-dimensional space, and it's going to have x and y components, as you can see in this picture. But at every point in time, right, so if I start here, right, I can take a snapshot, and every instance of time, say this is t1, this is t2, this is t3, right? It's gonna keep going, right? Okay. So this is all we mean by x equals xt, right? X equals x of t. So it means that x is a function of t, and y is a function of t, where t is going to vary between a and b. Okay, good. So that's how we describe a curve in the abstract. How do we compute a derivative? Well, a derivative is going to be the derivative, how do we describe the integral? Well, the integral of f is going to be defined over a curve, right? So I just described a curve C. This is a curve C, a generic curve C. We're going to integrate this curve, we're going to integrate this function over this curve, and instead of dx or dy, we're going to use ds. So what is ds? Well, you can basically think of it as if you have a curve, you're going to have a secant, right? A secant line. So think of that s as a secant, dsecant, okay? And as we move, that secant line is going to change. Okay, good. So how do I define this integral? Well, it's equal to the limit, right, where I'm taking a sum of the function times this little change in s, right? This little thing like that. And this is just standard calculus tricks, right? You make finite choppings of a space. You take a curve, you chop it up finitely many times, you make a definition, and then you take your limit and set it equal to infinity. You take it to infinity. So that's exactly what we did here. Well, this is maybe not very practical, right? By the way, what is the star here? xj star or yj star? The star is just like we said previously, where you have some sort of grid and you have to pick some point in the grid, some x point, some y point. It doesn't matter which one you pick. So again, that's what we're doing here. But practically, how do we carry this calculation out? Well, the integral of f along C is going to be the integral of f from a to b, where a and b were given in our parameterization, right? Well, how do we code the curve into our equation? Well, that's where xt and yt come in, right? So this is xt and yt as the curve C is defined, right? So this is xt on the curve, yt on the curve, right? So what value of x is this? Well, whatever value of x it is at that given value of t. But notice, this is a function of x. This is x as a function of t. So ultimately, it is just going to be everything in terms of t. There is no x, it's just going to be t. And that right there is going to tell us everything we need to know about the curve. It's going to basically just be the curve, okay? This right here is the delta S thing, right, in calculus world, right? And then you have dt at the end, right, because it's changing with respect to t, okay? So why does this equation make sense? This is just your Pythagorean theorem, right? A squared plus b squared equals c squared. So this whole thing right here is your c, right? Because to solve for c, I take the square root. So the square root of a squared plus b squared equals c. And that's effectively the tangent line, right? Why is it a tangent? Well, a secant line taken to its limit is just a tangent line, okay? So stay tuned for the next video, and we're going to get into some actual calculations.